Thank you again. Thank you. So next presentation will be given by Öztürk. I hope I pronounced it properly.
It's okay.
She's a researcher at the University of Siegen in Germany, working on ultrafast laser matter interaction and nanoscale surface structuring. She has a background in physics, and her research focuses on laser-induced periodic surface structure and the non-equilibrium dynamics induced by femtosecond laser excitation. She uses advanced X-ray scattering and diffraction techniques, including grazing incident methods at Synchrotron and at X-ray free electron laser facility to probe surface and subsurface dynamic with high temporal and spatial resolution. So she is giving a presentation titled How X-ray Scattering Let Us See Ultrafast Dynamic in Solid.
Yeah, thanks a lot, Alessandro, for the introduction. And good afternoon, everyone, or good evening, I don't know, depends on where you are. Today I want you to show how the X-ray scattering allow us to visualize the structure and dynamics on the lengths and time scales where materials actually work. How do we see can we watch the atoms move? I mean, if it is a frozen atomic lattice, it is not difficult. We could image them. But for example, when it is in thermal motion, many of the most important processes in the materials happen faster and smaller than we can see. But we can see them if we use X-rays. As you know, today is the 4th day of the school, so you already have many information about the usage of X-rays. Let me start with something very familiar, photography. The first successful photographs like this type from the 1840s required exposure times of several minutes. They gave us structure, what things look like, but absolutely no information about the motion. It is just a static structure image. And a few decades later, we have these famous horse images by Muybridge. This answered the simple but difficult question, a deep question. Do all the horses leave the ground at once? So the key advance here was shorter exposure times, and then this allowed motion to be broken into discrete frames. So now the exposure times decreased to few milliseconds, and this allow us to have the motion even if it is broken in discrete frames. Finally, in 20th century, in 1959, this photo is from Harold Edgerton, showed that with sufficiently short light pulses, motion can be completely frozen, even if the events lasting microseconds or less. So here you see the transient states of balloons. And this is exactly the same challenge we face in material science. Atoms move on extremely short time scales, and if our probe is too slow, we only see an average. But to understand, to see the dynamics, we need to probe both spatially and temporally, and precisely. And then I came to X-ray scattering. What does X-ray scattering measure? At its core, X-ray scattering is very simple actually. X-rays interact with the sample, with the electrons in the sample. And what we measure is how the electrons are arranged in space. But we don't see this directly in real space, but in reciprocal space. And we don't see the individual atoms, I mean, directly. Instead, we measure their correlations and how the density changes over different length scales. And the detector, I mean, different kinds of detectors exist, and the detector records intensity as a function of the angle. And those angle corresponds to specific real space distances in the material. At the end, I can have an image of the a real space image of my atoms. And then there are, of course, different scattering regimes probing different length scales. One of them is small angle scattering. Here you can see it. It is for the angles less than 10 degrees. And as short, we use SACS for it. SACS probes structures that are large compared to the atomic scale, typically from a few nanometers up to hundreds of nanometers. And because the scattering occurs at very small angles, SACS is sensitive to overall sizes, shapes, and spatial correlation of particles, domains, pores, or density fluctuations in the materials. Therefore, it is widely used, SACS is widely used for soft matter, for nanomaterials, and disordered systems. Another type of scattering is VAX. It is wide angle scattering, where the angle is larger than 10 degrees. And VAX accesses much larger scattering angles. And this corresponds to much shorter real space length scales. Therefore, this makes VAX sensitive to atomic arrangements, crystal structures, lattice spacings, and phase transitions. Then, in other words, we can say that VAX tells us how atoms are ordered and how that order changes during the processes such as heating, deformation, or phase transformation. And another technique is grazing incidence small angle X-ray scattering technique, with in short GZAX. This combines the length scale sensitivity of SACS with surface sensitivity. By eliminating the sample at very, very shallow angles, the X-ray probes only the near surface. And thin films it's mostly used for thin films because you can probe with these very shallow angles the thin film regions easily. GZAX is therefore ideal for studying nanostructures, roughness, pattern information at surfaces and interfaces also. And why do we need X-ray scattering in addition to X-ray spectroscopy, which you already saw yesterday and today? So, as I said in the previous lectures, you have seen X-ray fluorescence and X-ray absorption, which are incredibly powerful techniques. They tell us what the elements, elemental composition, what elements are present in the sample, and what the local atomic and electronic environment looks like, what is the chemical states. So we get the local information. However, they are fundamentally, as I said, giving information locally. Scattering is sensitive to special correlations, and the spectroscopy techniques like XRF, XAFs, they don't directly tell us how the atoms are arranged over long distances or how the arrangement involves collectively. This is where the scattering comes in. Scattering is sensitive to special correlations, as I said. Tells us how many atoms act together, where there is a disorder, where there is periodicity, if there's any emerging patterns you can see by scattering. And in modern experiments, in most of today's experiments, we almost always combine spectroscopy and scattering to get a complete picture. So we can think it like that. Spectroscopy tells us what atoms are present and their local state, and scattering tells us how atoms are arranged and correlated in space. And what is time result scattering? If we add time to the scattering, what happens? Up to now, what I showed you, what I discussed was static. It's like a single snapshot of the structure. But in time result scattering, we add a second clock. First, a pump laser excites the material. For example, you can use an optical laser, infrared laser. Then, after a controlled delay time, we probe the structure with an X-ray pulse. So then, by repeating the experiment for many different delay times, we reconstruct how the structure evolves in time. Effectively, it's like creating a movie instead of snapshots. Importantly, I can say that the pump and the probe do not need to be the same. The pump, as I said, could be an optical laser, while the probe is X-ray, giving us the atomic and nanoscale sensitivity. It's like that. If we give some specific examples, let's say you have a gold thin film, then you pump this gold thin film with your optical laser, a powerful optical laser. Then let's say after 100 picosecond, you probe it with X-ray and see what's happening on your detector. Therefore, as you probe with the X-ray, you have the atomic and nanoscale sensitivity. So, what can we learn from these dynamics? What kind of dynamics can we see in this experiment? By ultra-fast heating, we can shift the atomic spacing of the sample, and then this means you have the change in the position of your Bragg peaks, which shows you if you have a lattice expansion in your sample. Or by melting and maybe a recrystallization on pico and nanotime scales could look like a disappearance and recovery of diffraction peaks. Therefore, you can say you have a phase transition. Or after you pump your material, you can have a transient loss or re-emergence of some structural correlations. And then this will change your diffuse scattering and peak widths. Then I can say, okay, I have disorder, or I have order, or I have a transition from disorder to order. And after your probe, after pumping with the optical laser, you can have some periodic modulations of the electron density. And this will result in new scattering features. And then you can say how your density is changing. Therefore, if we use a time results scattering experiment, this scattering detects how the structure evolves in time, not just the final state, but how it is happening. And all of these processes could happen after a single femtosecond laser pulse. And then every laser pulse leaves a distinct fingerprint in the reciprocal space. And when we follow these fingerprints in time, we reconstruct the dynamics. We see how the structure evolves in time. As I said, for GZAX, with GZAX you can see the subsurface or surface, and especially thin films are used with GZAX. Why is this so? Because let's say this is our sample, and you are probing your sample with a shallow angle with the X-ray beam. Then what happens at the surfaces or interfaces? The symmetry is broken and atomic coordination change. As a result of this, electronic, structural, dynamic properties can differ strongly from the bulk behavior. So we have a surface sensitivity. And at shallow incidence angles, X-rays penetrate only a few nanometers here, I mean maybe tens of nanometers, and this makes grazing incidence geometries sensitive to the surfaces and thin films. And many functional phenomena emerge at the interfaces. Therefore, interfaces are also very important. What do I mean by interfaces? Let's say you have a silicon substrate, and on top of your silicon substrate, you have a titanium layer, for example. So there's an interface in between, and this is really important. Many things are happening here at the interface. Some patterns could form, electronic and optional optical properties could change. Therefore, probing at grazing incidence at shallow angles allow us to isolate and follow the surface-specific dynamics. These top layers, I mean, from a few nanometers to tens of nanometers. And what is changing from an equilibrium state to an extreme condition? What do we mean by extreme condition? So if we define the gentle excitation first, the energy deposited is small. The system responds linearly, stays close to the equilibrium, and standard equilibrium concepts like temperature, static structure remain valid. But what happens if I have a strong excitation? What do I mean with strong excitation. We push the system far from the equilibrium. Electrons can be excited much faster than the lattice or spin system can respond. And therefore, you have a non-equilibrium state where different degrees of freedom are no longer in balance. And we have entirely new transient phases. This is precisely where ultrafast lasers are becoming essential. Their extremely short pulse duration allows us to initiate these non-equilibrium states and track the evolution in time. So by using the ultrafast lasers, I can access femtosecond to picosecond time scale, and I can initiate and control the non-equilibrium dynamics. When we combine this with synchrotron radiation or X-FEL probes, we can directly observe how structure, charge, and dynamics evolve in their natural timescales. So if I use an ultrafast laser, this enables me to make a pump probe experiment with synchrotrons and X-FELs. And in short, I can say ultrafast lasers are the gateway that allow us to move from equilibrium physics to exploring extreme, transient, and maybe hidden states of the matter. So now let me show you one example where the scattering method shines. This is an experiment we did at European X-FEL. It is the picosecond surface morphology in femtosecond laser irradiated metals investigated by grazing incidence X-FEL. Now it seems a little bit complex, and it might sound frightening, but actually I will try to explain it very, very briefly. So let's say we have a sample, and then we shine this sample with femtosecond laser. And then what happens after the laser irradiation? I mean, we are checking the 10 to 100 nanometer thickness from the surface. So what happens? Laser is absorbed by the electrons in the sample in femtoseconds. Then a phase transition, maybe a plasma state, starts in femtoseconds to picosecond time scale. Then thermalization with lattice and ions takes place for the times larger than picoseconds. And if we wait longer from picoseconds to nanoseconds, surface ablation could happen if the laser is powerful enough, and expansion could exist. And afterwards, after nanoseconds to microseconds, resolidification could occur. And here you see, for example, a new structure forming on your surface, which is called LIPS, laser-induced periodic surface structure. So what happens if we look closer when we heat our sample with ultrafast laser? As I said, in the first few femtoseconds, there's a light-matter interaction. The femtosecond laser hits our sample, hits the solid, energy is absorbed by the electrons only. Then we have hot electrons, and this causes a highly non-equilibrium electronic state. Then the lattice is cold, and ions cannot respond on femtosecond time scales, so crystal structure remains unchanged initially. But afterwards, energy is flowing, and electron and phonon coupling transfers energy to the lattice in picoseconds. So lattice starts to heat and move. And at the end, you have a non-equilibrium matter, and you can reach a transient state, which is normally not accessible in equilibrium. So first, the electrons react to our ultrafast laser. Afterwards, lattice follows this, and we reach a non-equilibrium state. And what does scattering add into this picture, into this story? X-rays do not take the pictures of the atoms, but they reveal how the matter is organized. And why do we need scattering here in this pump probe experiments? Because laser excites the system, and this gives us ultrafast changes. Changes happen in, as I said, in femtoseconds to picoseconds and over nanometer length scales. Therefore, we need a probe that can see below the surface and follow the structural changes in time. So the right tool to do this is the grazing incidence X-ray scattering, GSAX, combined with an XFEL, and GID, grazing incidence diffraction, combined with an XFEL. So with GSAX, we can track the density changes below the surfaces. We can see the multi-layers, interfaces, and via GID, grazing incidence diffraction, I can track the surface shape and atomic order and see what's happening in time after excitation. Therefore, in summary, I can say, when you have a sample and when you pump your sample, which means when you shine your sample with an ultra-fast laser, optical laser, and when you use an X-ray scattering to probe this, we can watch the structure evolving while it is happening at the surface and at the interfaces. So then what is, very, very briefly, what is an X-ray free electron laser? Actually, on Monday, you had a lecture and where in some part of the lecture, you already saw XFEL. But here, just as a reminder, I can say a few words. As an X-ray free electron laser, the electrons to generate laser-like pulses of light is in the X-ray wavelength range. We can energize electrons by accelerating them, making them move in one direction at a speed ever approaching but never quite reaching, of course, the speed of light. So we have an electron gun, then we have a linear accelerator where we make them move in one direction and accelerate them And by using a metallic structure called a cavity, or which can also be called resonator, we accelerate these particles. And when an intense electromagnetic field is applied across the cavity, a particle carrying an electric charge, such as an electron, is moved through the surface, and this happens at an increasing pace the more cavities are used. So, for example, at European XFEL, which is stated in Hamburg in Germany, the accelerator currently uses nearly 800 cavities, and it is nearly 2 kilometers in length. And the European XFEL accelerator can currently energize electrons up to nearly 18 gigaelectrovolt. So, what happens? What is the principle of free electron laser? The accelerated electrons race through a so-called device ondulator, and periodic arrangements of the magnets here force the electrons onto a tight slalom path. In the process, each individual electron emits X-ray radiation that amplifies more and more. And this amplification process is induced by the interaction of X-ray radiation with the electrons. Because the radiation is faster than the electrons speeding along their slalom path, the radiation overtakes the electrons flying ahead and interacts with them along the way, and accelerating some of them or slowing some of the others. Therefore, in principle, electrons interact with periodic magnetic fields of the undulator magnet to build up an extremely short, intense X-ray pulse. Brilliance is a very important parameter for the XFELs. What is brilliance? Brilliance tells us how many photons we have, but how well they are concentrated in space, angle, and energy. And it is defined as the number of photons per second, per unit source area, per unit solid angle, per relative bandwidth, typically 0.1%. So as you see in the formula, the numerator is simply photons per second, and in the denominator we normalize by the beam divergence in milliradians squared, the effective source area, as I said, in millimeters squared, and spectral bandwidth. What this means is that a source is brilliant if it delivers many photons that are tightly collimated and come from a small source and are spectrally narrow. This is why brilliance is much more meaningful than raw flux when we care about coherence, focusing, for example, in SAX or coherent imaging. And here in this plot, you see the historical evolution of the average brilliance over more than a century. We start with X-ray tubes, then we move through first, second generation, and third generation of the synchrotron sources. Then this leads to orders of magnitude increase in brilliance, and facilities like ESRF, already represented a dramatic leap compared to earlier sources. And here in this plot, you see this even more by comparing different radiation mechanisms. Bending magnets improved things, yes. Wigglers pushed it more. Undulators gave another huge jump. And finally, free electron lasers increased the peak brilliance by many orders of magnitude further. Therefore, free electron lasers don't just give more photons, they give extremely short and coherent pulses, which fundamentally changes what experiments are possible. It's not just brighter, it is more controlled, more focused, and more powerful for more precise work. This is why modern synchrotrons or free electron lasers are revolutionary. It explains why we can now do experiments that were previously impossible with the earlier X-ray sources. And how extremely fast X-ray pulses really are. So if you think of a bird's wing, that happens on the order of a millisecond. And even high-speed photography operates in the microseconds range. A typical camera shutter is around 100 microseconds, and even a photographic flash is only tens of microseconds. If we move down, important biological processes like proteins happens much faster. Protein folding, for example, on microsecond time scales, and molecular group motions are in nanosecond regime. These are already far beyond what conventional imaging techniques can resolve directly. Going further, we reach atomic motion. Atoms vibrate on the scale of hundreds of femtoseconds time scales, and electrons move on femtosecond or even sub-femtosecond time scales. This is the natural time scale of the chemical bonds and electronic structure. Therefore, this is where the X-ray lasers are coming in. Modern X-ray free electron lasers produces pulses with duration of few femtoseconds. This is short enough to effectively freeze an atomic motion. Compared to millisecond time scales, this is almost 1 trillion times faster. And X-ray pulses are not just short, but they are on the fundamental time scale of atoms and electrons. So this allows us to make true movies of structural dynamics and phase transitions, chemical reactions, non-equilibrium processes, as they actually happening in these time frames. So therefore, I can say femtosecond X-ray pulses give us access to a regime where the structure, motion, and function are directly connected in time. So yeah, here you see the difference in pulse length, energy range, and number of photons per pulses for XFEL And for a synchrotron radiation, these are taken from ESRF. And for XFEL, we can say we have coherent, short, bright, narrower bandwidth. And yes, it is less stable. For synchrotron, it's relatively longer. It has a broader bandwidth, and it is much more stable than XFEL. So in reality, how does it look like? This is a photo of XFEL, which is, as I said, in Hamburg or close to Hamburg, Schenefeld. So here is DAISY. This is the synchrotron facility DAISY. So the injector at DAISY is used. Then we have a linear accelerator of 1.9 kilometer. And then you have here at Schenefeld the experimental hall of European XFEL. So the electrons are injected from here, and the experiments are done here 2 kilometers away. So what does grazing incidence small angle scattering looks like, basically? So we have a sample, and then with the grazing incidence, the X-ray is coming, and then we have a detector, and on this 2D detector, you have your image of scattering. So GSAX gives information about the surface morphology dynamics. You don't make a angle scanning usually, and you mostly check the weak diffused scattered pattern in two-dimensional detector. And you can track the structural evolution via pattern changes. This image here changes if you have a structural change in your sample. So you can have an out-of-plane scattering and in-plane scattering. These both give different information. Out-of-plane scattering gives information about the roughness and depth profile, while the in-plane scattering gives me information about the size, shape, and correlation length. So basically, GSAX answers how does the subsurface structure change after laser excitation? How do multilayers expand, melt, or reorganize after laser excitation? And grazing incidence diffraction, GID, it is a similar geometry, but this time you put your detector somewhere a little bit far away, and you require precise angle control. Again, the X-ray is coming from that side, from right, and it is scattered. Here you have your detector. So sample and detector are scanned to hit diffraction conditions. And the signal appearing on the detector at well-defined angles, not at every angle, but at well-defined angles. So you can have discrete spots or lines depending on your sample. Then when you make the analysis of this diffraction pattern, you can see the sharp, intense peaks here, this peak, this line, and you have a lower background and you have a high angular resolution. By this way, you can track the peak position, width, and intensity. You can characterize the crystal structure of your sample. You can obtain the unit cell dimensions. You can obtain information about the purity of your sample. So basically, we answer these questions with GID. How does the surface crystal structure respond? Does the surface melt, disorder, or recover? So now, at the end, this is our experimental setup. Now, what we have? We have a silicon substrate, and on top of the silicon substrate, we have a gold film, which is 50 nanometer or 100 nanometer. And then what do? We probe the sample with an optical laser, with an infrared laser. This red one is the optical laser, which is probing, which is heating our sample. It is nearly vertical to the sample. And then with a certain delay, we probed what is happening on the sample after heating with the pump laser. We probe this with X-ray, a free electron laser. We send the X-ray with a shallow angle, with a grazing incidence angle, here 0.7 degrees. Then we have three different detectors. One detector, this one, is for GZAX. The other two are placed according to the angles for GID. So from this detector, I get the information for 111 diffraction plane. For this one, from this one, 200 plane. And from this one, I get the GZAX image. So GZAX measures how the overall scattering pattern changes. GID measures how specific diffraction peaks move and change in time. So I don't get into details, but this is for example, GZAX image. These are also GZAX image. What is the difference between them? So the first one, this one, is before the optical laser. So without any pumping, you see this image. But after pumping your sample, after you heat with an ultrafast laser, 10 picosecond later, I probe it with X-ray, and I see there are some fringes here. You see? These ones. They don't exist here before heating. And then, if I continue, 30 picoseconds later, these fringes looks more pronouncedly. And even after 100 picoseconds, these are much more pronounced. So when I plot these in this direction and in this direction, I get different information. From the slope of this, I get the information about the roughness of my sample. So after pumping, my roughness is changing, it is increasing. After pumping, I see some new correlation peaks here, which means I have some nano islands or gratings appearing in my sample. And from the GID measurements, what do I see? This was before the heating, before the pump laser. After the pump laser, we have here a much more pronounced ring in the GID pattern. So if we draw this line out, sorry, if we draw this line out, I see that the peak starts to appear at even 1 picosecond delay, and the Q position is shifting to higher Q, which means my lattice is compressed after laser excitation. So what do I learn from this? The crystalline domains begin to reorient themselves after the heating, after the laser pumping, within a very short time scale. With GZAX, I get the information about the density distribution below the surface. I see the subsurface. I can see the growth of nanoscale fluctuations. On the other hand, with GID, I can see the atomic motion of at the surface. I can see the top atomic layers. I am sensitive to, surface sensitive. I can see the elasticity, lattice stability, surface reconstruction, the strain, the disorder, if there exists melting, maybe. Therefore, GID gives me the ultrafast atomic order at the surfaces, while GISAX tracks the nanoscale density and morphology beneath them. And when we combine these two techniques in situ, we get a complete picture of the ultrafast structural dynamics. So let me wrap up with the key message here in this talk. X-ray scattering gives us access to structural dynamics on ultra-fast timescales, but what we measure are the changes in reciprocal space, not in the real space. And ultra-fast X-ray scattering does not produce movies, but it provides quantitative constraints that, together with theory, allow us to understand and ultimately predict dynamical behavior in the materials. Here you see inside our vacuum chamber, this red one is our laser, which pumps the sample. The sample is here. And here on the other side, the blue one is the X-ray coming to your sample in grazing incidence. So they have to be perfectly on the same spot. And here you see an optical microscope image from the samples, from the real samples. For these circles are because of the laser impulse, so they are burned. And these lines are the X-ray probing. So this means the first one is fine. There's an overlap. We can use this, for example. This one is perfect. This one is, yeah, not so good. But then, for example, this one, we are hitting the pump laser at this point, but we are probing here. So I cannot use this information from this shot or from this one. But here we have a perfect overlap. I can use this data, or I can use also this data. So it needs a very precise overlapping, also in time domain and in a spatial domain. So it's a very challenging experiment, but I get many different information from this experiment. So this was a big collaboration, of course, many different institutes and universities from different countries, as you see, from Germany, from Japan, from France, from Korea, from United States. So thanks to all our collaborators. And if you want to get more information, or if you want to ask something, you can reach me from our website, our group website. We are in the physics department, X-ray science group. This is our web page, QR code, and this is our LinkedIn QR code. So you can follow us and see what we are doing, what we are measuring, where we are. So thank you for your attention.
Thank you very much for your presentation. Very interesting. We have a few questions.
Yes.
Maybe we try to address all of them because you are the last speaker and then you cannot reply in the chat. Okay. Okay, so first question is, how do you practically handle the synchronization challenge between femtosecond laser and X-ray pulses at grazing incident geometry? And then there is a comment to this, synchronization to fundamentally random nature of self-amplified spontaneous emission of FEL.
I couldn't hear the last part, sorry.
So the synchronization to the fundamentally random nature of self-amplified spontaneous emission of FEL.
This is really something very, very hard and takes really time. It is very challenging, but at XFEL, at European XFEL, there's a perfect beamline scientist staff. So they manage this. They have a perfect overlap. Of course, we have to check it always because, as I said, it is not so stable as Synchrotron, but you have to check before the measurements and see if you still have an overlap and correct if there's needed. But I can say that, let's say if you have a beam time of 1 week, for the first 4 days, you can spend with these alignments, with these overlaps.
Okay, so it's quite challenging. Okay, then with such intense pulses, how do you distinguish between laser-induced dynamics and sample damage, especially for delicate surface or thin films?
Okay. First of all, we also have post-mortem microscope images. We can see from them if you burn your sample, if you really damage your sample, you can see that. And if you damage your sample, so you see nothing. I mean, your data shows that you don't have these gratings or you don't have these diffraction peaks, or let's say if you melt your sample, you can see from your diffraction pattern that this peak is coming down, meaning that you don't have it anymore. You have a melting, you lose your crystallization. Therefore, by looking at your data, you can discriminate what is a structural dynamic and what is burn of the, let's say, laser.
Okay. Does the current time resolution with X-ray reach the attosecond time scale? I recall reading a recent manuscript on a diffraction experiment on graphene dynamic performed at attosecond resolution laser.
Yeah, this. I mean, I mean, this is true. They are using also attosecond lasers, but for the moment, for us to see the dynamics, femtosecond lasers are enough. Therefore, we are using this facility and we are using this laser.
Okay. Aside from the strong influence of the pump, can we detect the weak intrinsic atomic breathing without even gentle excitation of the sample?
So as far as I understand, if not a ultrafast laser, but a gentle excitation, can we see the dynamics? Yeah, why not? We can see, but if it happens, of course, because if you have a gentle excitation, sometimes you don't see anything. You don't have this transformation, or you don't have this structural dynamics happening. For example, or it could happen in longer time scales. You have then you don't make it in picosecond or nanosecond, but you have to wait longer. But this is a different experiment then.
Mm-hmm. Then how can we quantify the affected density, such as dislocation density from GIS AXS in epitaxial film in bulk or in nano or micro scale, right at the interface between substrate and film? And what is the minimum spot size we can achieve for a GIS AXS epitaxial film structural analysis?
So, by using the angle of incidence, I mean your grazing incidence, you can calculate the penetration depth. So you can see where you are probing with your X-ray. So then you can see if you are probing the interface or you are probing the surface or subsurface. And also, depending on the time, of course, the heating moves down, flows down, and the lattice becomes also involved. And then you can also calculate this from the time scales and decide where you are seeing, I mean, where you are probing with the X-ray. And there was one more question, but I don't remember.
Yeah, there is another question. I think it's the last, at least the ones that I saw in the chat. So is it possible to control the measurement, the process environment, such as doing experiment under nitrogen or argon gases?
Yeah, you can. You can.
Okay, thank you. So
Welcome.
we finished perfectly in time. I didn't see any other questions. So if you have other questions for the speaker, you can contact her by email. So thank you again for your presentation. I would like to thank again all the speakers of today and also ICTP staff for their support. And the appointment is for tomorrow for another day of the school. Bye-bye.